Welcome to part 7 of the Dueling AI self-play reinforcement learning series. In this video, we are going to go ahead and get back into the agent class and hopefully get a training loop going. So let's get started. To begin with, we are actually going to go to train.py and get a little bit of housekeeping set up here. So one of the things that you want to be able to do is change different variables throughout the process. So you want to set those variables in the calling script. You don't want to set them in your final class. So let's go ahead and we're going to set up a few things. We're going to do 500 episodes. Later on, this will turn into more. We'll do max episode steps is 2,000. We'll do total steps. Actually, we don't need that variable here. We'll do batch size is 32. That seems to be the one that works the best. Learning rate will be 0.0001. Epsilon will be 1. Min epsilon, I found worked really well a little higher than usual. I would usually set this to 0.1 for most reinforcement learning projects, but this one seemed to work out a little better at 0.15 with the self-play example. I think having it have a little bit more randomness as it was only playing against itself, it helped it a little bit. We'll do epsilon decay, how quickly that randomness is decaying, as 0.995. Gamma will be 0.99. Max buffer size is going to be 200,000. The reason we're setting this to 200,000 and not a million or something else, other than just memory pressure, we want it to be a little bit faster than that 200,000, is we actually want our buffer to refresh as the opponents change. So it's going to start off, it'll be a little bit of a leapfrog. You can think of, if you think about the way that our agent's going to learn. So we'll start off with, you don't have to type this part out, but I just want to explain. We're going to have a live agent, and we'll call this V1. And then we're going to end up with a series of previous agents. So prev agents. And at the very beginning, so at step 1, V1 will just be copied. So it'll be the agent playing against itself. After 100 episodes, this will be V2. And assuming this is improved, this will be V1 and V2. After a whole bunch of episodes, we'll just pretend like it's only up to 3 or 5. This will now be playing against the last 3. So it'll be playing against V3, V4, and not V5 yet. It'll be really playing against V2, V3, and V4. And when V5 can consistently beat these 3, then it'll get added to the queue and we will move. We'll play against, then it'll be V6 against V3, 4, and 5. The reason I'm going into that is you actually want a slightly smaller buffer. If you have a massive buffer, then you're going to be down here, running V20 of your agent, and it's still going to be pulling in transitions from version 1 and version 2. And since version 1 and version 2 aren't going to be very good, it's a terrible player at that point. It's just doing random things. The things that your version 20 agent are learning from version 0 and 1 are not great. So you want to kind of stair-step this and make sure that your buffer size supports that stair-stepping pattern. All right. We're going to do a target update interval of 10,000. We'll do checkpoint pool. So this is the number of previous agents that we're going to play against will be 3. And hidden layer will equal 756. All right. One of the things that I like to have just to capture these things is a start time and end time. So let's go ahead and get that in here. We will import time. And down here, we're going to say start time is equal to time.perfCounter. And then at the end, we're going to say end time is equal to time.perfCounter. And then elapsed time is equal to end time minus start time. And then we'll just say training run completed in elapsed time seconds. Okay, let's go ahead and make sure this works. Okay, cool. My train.py is what's getting called. I just want to make sure that I don't have any errors before we go any further. All right, we're creating agent with the device CUDA. And it should be exiting. Let's see. I don't recall. I may have added a sleep. Yes, I did. I added a sleep in order to test something in a previous video. And I don't recall what that was. Okay, but we got training run completed in 30.58 seconds. All right, let's go back to our train.py. Again, just kind of testing things as we go. One of the things that we're going to want to set up is some logging. So we are going to need a name for our log. We're going to do a summary writer prefix. And in the class, the summary writer, the logger, is basically going to, it's going to put out a log with a timestamp on it. The summary writer prefix is really for what we want to capture for information about this run. So let's say you were testing a series of different learning rates. You might want learning rate to be part of your summary writer prefix. So let's go ahead and actually let's make it a suffix. We will do our string here, and I'm just going to call it DQN as the name, and then LR equals learning rate. And we'll do BS equals batch size. And again, in this case, I don't actually care about any of these because I know what parameters I'm going to be playing with. As you tweak params, if you want to try a bigger batch size, different episode steps, a different, epsilon decay, then what I would do is I would add them to this, and then it's going to put them in the name of the logs. If none of this makes sense, that's fine. You'll see how it plays out later. Let's go ahead and pass in all of the variables that we have just finished defining. So hidden layer equals hidden layer. Learning rate equals learning rate. Gamma equals gamma. Max buffer size is max buffer size. And again, we're just getting all this out of the way. That way, when we get to coding up the agent, we've got all our variables. We don't have to do any of it later. We'll do target update interval equals target update interval. Max episode steps is equal to max episode steps. Epsilon is equal to epsilon. Min epsilon, so the minimum we want to allow it to go to is min epsilon. Epsilon decay is, of course, epsilon decay. And checkpoint pool is equal to checkpoint pool. All right, so we've got all of those variables out there. We're going to need a call to agent.train, but first let's go make sure we have an agent.train. All right, we do not yet have an agent.train. So let's start defining agent.train. And then we will actually, let's first just run this again, make sure that there are no unknown variables. There aren't. We're finishing in a half a second. That's exactly what we expect. So we're in a good place. All right, let's go down to our train method. So in agent.py, you're going to def train, and train is going to take self, episodes, summary, writer suffix, and batch size. And from a design perspective, you might be wondering what led to putting some of these variables down here in train and some of them in agent, and setting them as self dot, frame stack or frames or environment. There are certain things that I found if you end up in an environment where you need to do multi-step training, batch size, episodes, those have come in more commonly for me, but there's nothing saying that you couldn't put those variables up here. This is just easier for the scenarios that I usually run into. All right, so let's go ahead and define our summary writer. So summary writer name is equal to runs / datetime dot date time dot now, and we're going to do str ftime. And in this, you're going to have %y dash %m dash %d underscore %h for hours dash %m for minutes dash %s for seconds. And then at the very end, we are going to do underscore and summary writer suffix. Okay. And then we will define our writer is equal to summary writer and summary writer name. All right, and it looks like I have not yet imported summary writer or datetime. So let's go ahead and import datetime. And from torch.utils.tensorboard, import summary writer. Okay. Let's go ahead before we go any further, and we're going to go get a call to agent.train in here. So we're going to do agent.train, and if we go back over to our, actually, I'm just going to open this up over here. The text will be a little small. That's okay. All right, so over here we accepted episode, summary writer suffix, and batch size. So over here, we are going to do episodes equals episodes, summary writer suffix equals summary writer suffix, and batch size equals batch size. All right, so let's run this and just make sure we don't get any errors at this point. And again, training run completed in half a second. So we are in a happy place. All right. So let's continue on with our train method. We have our writer. And again, this is just a logging thing. This is going to give us a way to use TensorBoard in order to show logs that tell us how we're doing. And I will pull that up as soon as we have something to log to give you an idea of what to expect. So let's go ahead and say if not os.path.exists models, we are going to os.makeDirs models. And I bet we don't have OS either. So let's just go ahead and import OS. Okay. And that'll be our spot for storing our models. We are going to define a total steps So this is just going to track how many steps we've taken in the environment. And then we can go ahead and do player. We actually don't need the checkpoint code yet. We'll get to that later. Let's go ahead and just say for episode. Actually, we do need one thing. Best AVG score, best average score is -100. And I'm not starting at 0 because we're actually going to average below 0. So we're going to add some logic later that says something like if score greater than best average score, then update best average score. If you set this to 0, it will never update because it's going to take us a long time to get above 0. So let's say for episode in range episodes. So now we're finally starting our training loop. We will set done to false, done equals false. We will set player 1 episode reward equal to 0. Player 2 episode reward equal to 0. And then we're going to go ahead and call our environment. So OBS info equals self.env.reset. I'm going to add okay, we already have our process observation. So we're going to say observation equals self.process observation, OBS, and we're going to pass a clear stack equals true in here. We will set episode steps to 0 because we've taken no steps yet. And we're going to do episode start time is equal to time.time. And then we'll say while not done, and episode steps is less than self.max episode steps. That's not auto-filling. I wonder if we set it. We probably didn't. So let's come up here and just go ahead and set max episode steps. So we'll set that right below model. Okay. So while we are less than max episode steps, we're going to run. And we will do player 1 action. And what we're going to do here, there are a few different ways you can handle this. We could start off right away with self-play. But self-play is a little bit more complicated. It is something, there are more things that could go wrong. So what I recommend doing is actually starting with playing against one of the bots, and make sure that learning works in a basic you against the bot or your AI against the bot kind of environment. Because if it doesn't work there, then it's not going to port over to self-play. So we're going to start out just doing sort of your standard RL loop versus the bot. Our environment supports both. And then we will move over to doing reinforcement learning, in a self-play architecture a little bit later. So we're going to say self.get. Ooh, we don't have a get action yet at all. So let's go ahead and work on get action. This, by the way, is the downside of writing code and then waiting a while to talk about it, is forgetting which parts you have completed and which parts you haven't. So we're going to go ahead and define get action is self, OBS, player, and we'll default to 2. We'll need this later. Checkpoint model will be false. Episode will be 0. And eval mode will be false. We'll walk through where we need all of these a little bit later. So let's just say to do flip obs if player 2, to do checkpoint model, and then we can just pick up the basics down here. So if random.random, I bet I haven't imported random, from random import random. Actually, you know what? The way I'm using that, I just need to do import random. Okay. So if random.random is less than self.epsilon, then and eval mode is false, then action equals self.env.action space dot sample. Else, we want to grab our Q values of self.model.forward, obs.unsqueeze, 0.2, self.device, and we want to grab the 0th element. And then action, we can do torch.argmax, Q values, dim is equal to -1, dot item, and then return action. Okay. It also helps if I get all of this on the right level there. And we now have a get action that we can watch. So back up here to player 1 action, we can go ahead and start working through this. All right, so player 1 action. Let's give ourselves just a little bit of space there. We're going to pass in obs. We'll do player is equal to 1. We will do checkpoint model is false. We'll make this a variable later. And episode equals episode. Okay. We can go ahead and set player 1 reward equal to 0. We'll set player 2 reward equal to 0. And then we will do our next obs. We'll actually take the step. Next obs, player 1 reward, player 2 reward. Done, truncated, info equals self.env.step. And we'll be passing in player 1 action is equal to player 1 action. And then we're just not going to pass in player 2 action. And if you recall, our env step configuration should automatically handle that. It should successfully, go grab an action for player 2 if there is no action selected. So let's go ahead and run this and just see what happens. All right, agent object has no attribute epsilon. And by the way, we're definitely not at a functional place yet. We are at a place where I want to make sure that what we've written so far works, though. Okay, so we're going to do self.epsilon equals epsilon, self.epsilon decay is equal to epsilon decay, and self.min epsilon is equal to min epsilon. Okay, so it's running, it's doing something. It is taking a very long time, though, to do what it's doing. So what we're probably doing at this point is it should, because we don't have any logging, and it is running for, hundreds of steps. So let's go ahead down here and just go ahead and get some of our logging in place so that we have that. We'll do if total steps. Actually, we don't even want that yet. We want per episode logging for now. So we're just going to go ahead and print completed episode in, we'll do episode end time equals time.time. Okay, and then we will say episode time is equal to episode end time minus episode start time. Okay. And then we can say completed episode with player 1 score, player 1 episode reward, and then we will do player 2 score. Go ahead and track both. And episode time will be episode time colon 1F seconds. And over here, let's do episode time instead of episode Tim. And I have to actually close that off. And then we'll also do another print for episode steps will be episode actually, we haven't even tracked episode steps yet. Yes, we are. Yes, we have. But we also do need to add to it every time. So right up here, let's do episode steps plus equals 1. And down here, then we can log episode steps. All right. And I do need to close that off. Let's close this and rerun it and see if we get some results this time. Okay. We are successfully getting results, but we're not getting any real information. And we're not getting, well, we're getting seconds, we're not getting scores. And we're not getting scores because we are not successfully logging. So player 1 episode reward plus equals player 1 reward, and player 2 episode reward plus equals player 2 reward. All right, this is why we test things. Okay, so we now have what is, a mostly random agent. And our agent isn't learning anything yet. We don't have any learning steps. We're not decrementing epsilon. We're not doing any training, but it is running, and it is successfully playing games in about a second per game. And importantly, we also see these scores mirror each other. That's something we want to make sure we see. So if you see, both of them have a positive score, or they have, one of them has a 5 and one of them has a 4. That is inherently wrong. For player 1 to have a -3, player 2 must have a +3. That is how this game is set up. So make sure that those scores mirror each other, whatever the distribution looks like as you're looking at that. Okay, let's go ahead and start working on a little bit more intelligence here. So we've got our player 1 episode rewards. We've got our episode steps. We have not yet here. Let's do a few things here. Let's grab this, grab episode steps and move it down. Let's grab total steps plus equals 1. We need to increment our total steps. That'll be important later for logging. And then right after this self-env step, we need to actually store our transition in memory. So we're going to say self.memory.store transition. And we're going to do obs, player 1 action, player 1 reward, next obs, and done. All right, and let's just, and also before we forget, let's do obs equals next obs after that. And let's just go ahead and run this as is, because this is the first time we've tied the memory in for real, and I'd like to make sure that it is functional. Okay, we are successfully storing transitions, or I assume we are. We obviously haven't retrieved them yet, but we're not. It's not blowing up. It has not errored thus far. So finally, let's get into the training steps. So we're going to say, we can go ahead and kill this off. So for training, we're going to say if self.memory.canSample batch size. Then we're going to do observations, actions, rewards, next observations, dones equals self.memory.sample buffer and pass in batch size. And the reason I'm not abbreviating obs here is because we're ending it in a plural, and it just obses or next obses just feels like a strange variable name. I suppose I could have also done obs batch, and that would have been fine too. So we need to change some of our dimensions just a little bit. So we're going to do actions equals actions.unsqueeze, and that'll be 1.long. We'll do rewards is equal to rewards.unsqueeze, and that'll be a 1. And dones equals dones.unsqueeze, and that will be a, not flatten, float. We will define our Q values. So our Q values is going to be self.model, pass in observations. Our Q state action is going to be Q values dot gather 1 actions. So that is our Q values with the actions that we have selected. We will need our target. So with torch.noGrad, we're going to go ahead and say next actions is equal to torch.argmax and self.model next observations, and dim equals 1 and keep dim equals true. And then our next Q will be self.target model. We haven't defined our target model. Let's go ahead and do that. So let's go up here. And we actually need a few variables here that we haven't defined. So let's just go ahead and get them. So for target model, just copy model, and then what we're going to do here is we're going to say self.targetModel.load state dict of model, except it's not model, it's self.model. And then let's see. And in fact, it's not just self.model, it's self.model.state dict. Okay, so we've loaded our dictionary, and then we also need our self.optimizer is equal to optim.atom, and we're going to do self.model.parameters, and we'll do LR is equal to learning rate. Okay. And we need to go ahead and import torch.optim. In fact, we need to import a few things. So let's come up here to torch. So let's do import torch.optim as optim. And then I think we're going to need torch.nn.functional as f, a little bit torch, not toch. Toch is not a valid import. No surprise. All right, back down here, we now have a target network. Let's see, Q. Okay, we now have our target model, and we can say next observations dot gather one and next actions. And then we can say our targets is rewards plus 1 minus dones times self.gamma, not ampersand, times self.gamma, which we need to define, times next Q. All right, let's go back to the top. Let's remember we're on line 121 here. So we do need to go ahead and grab self.gamma equals gamma. Okay. So remember what we're doing here in Q-learning is we're basically getting our predicted Q values, and then we're using our target model as an anchor point, something that is going to lag behind the current model a little bit, provide it some stability. And what we're attempting to do is we're attempting to get the value of the current state in regards to the actual rewards. So the targets are going to be the rewards, and then this is going to see if it's done, this is going to be a 0. So 1 minus dones. If done is true, done will be a 1. That's what we're doing up here with float. So if done is true, done will be 1. So 1 minus 1, of course, 0. So if done is true, it zeroes out the whole right side of the equation, because you can't have a future state value if the episode is over. So we're taking our current rewards plus the value of the next value of our state times our discount factor, which is gamma. So what we're basically trying to do is calculate the value of the current state with a calculated value based on the calculated value of whatever the next state is, plus the actual value of the current state. Because if we just scored, well then, hey, the value of current state is 1. If we haven't, then it's, the predicted value or just the predicted value of our next state. So now we need our loss is equal to f.msc loss QSA and targets. And then we finally have something that we want to log. So we're going to do writer.add scalar. And this is basically a way to just add a value to our writer. So the first thing you want to do here is the label. So stats, and whatever you put before the forward slash will become kind of a category. So we're going to put this in the stats category, and we're going to call it model underscore loss. We're going to log loss.item, and we are going to put that in total steps. So total steps is going to define the x-axis of that graph. If you don't put total steps, or if you just put this as, say, 5, it's going to create a dot on our graph at 5 and never change. So this is going to show that value over time. If we continue on down, we are going to do self.optimizer.0grad. We'll do our backprop step, loss.backward, and self.optimizer.step. Okay. And then if total steps modulo self.target update interval is equal to 0, then self.target model dot load state dict self.model.state dict. And our target update interval, of course, is how often we want to update that that secondary or target model. And I'm realizing as well that let's just go ahead and get, we don't need checkpoint pull, but we can see that target update interval hasn't been used. And that tells me that we need to come down in here and do self.target update interval equals target update interval. All right. Let's go back down to our train method and continue on. So we're actually at a point here where we can go ahead and start logging our scores a little bit more. So we're going to do a writer.addScalar. And it's important to get this right along time with episode end time and the logging here. We're going to do training. Remember, the first section is the category. And we're going to say player 1 training. And we're actually going to end up with quite a few different metrics by the end of this, just because we're building a little bit of a more complex project. That's why I'm being careful to put these in specific categories. So we're going to say player 1 episode reward and episode. And then we'll do player 2 training. And again, these should mirror each other all the time. So let's go ahead and run this and see if we get any errors. Oh, and we did get some errors. So let's see. Torch.CUDA.floatTensor and weight type torch.floatTensor should be the same. That makes sense. They should. So what this means is basically that one of the things we have, either the input is on the GPU and the models on the CPU, or the other way around, the models on the GPU and the inputs on the CPU. One of those two things is happening. So I can see here that we didn't do anything at all with self.device on the model, but we did do it on memory. So let's go ahead and do a to device. And then at the end here as well, we're going to do .to device. And that's going to send both of these, the model and the target model, to the GPU. And again, if you don't have a ton of memory on your GPU and you want to run your model on or your memory on the CPU, if you're getting any out of memory errors as you're starting up your load here, or your run here, just change this to CPU on output device. But in this case, I wanted to stay on GPU. Okay, let's see. We got another error. 2 received an invalid set of arguments. Okay. It did not like something about what we just did. I assume. Let's make sure that that it's calling it at the right place. So yep, agent equals agent. We're doing it on self.model equals model. And it doesn't like our 2 here. All right, and I think the problem here is that instead of device, I need to do self.device. Let's try it again. All right, and we have a training run successfully going. Now at this point, it should also be giving us some TensorBoard logs. If you have something like VS Code, then the TensorBoard plugin is going to let you see those logs right there in VS Code. If you don't, then you're going to just run TensorBoard. So if I come over here and just close out of my editor, I can do, so the no-hup is going to send it to the background, as will the no-hup and ampersand combination. But the actual command is TensorBoard -- logdir equals runs -- port, and then whatever port you want it to run on. So I do want to let that sit in the background. Then I'm going to go pull up a browser. All right, I went to a browser. I have localhost :4444, and you're going to want to click on scalars. And then you'll notice over here, it's got every run that we tried as we were troubleshooting, because it, started a bunch of them. What I would do here is just hit toggle all runs to turn them all off, and then turn on our run here. So what you should be seeing over time is player 1 training should start to go down a little bit, or should start to go up, and player 2 training should start to go down, because remember, player 2 is our bot. It should be our easy bot. Let's go see. So there are a couple things that we probably want to check on as we're starting training here. So let's go grab our game.py and see if we had a default. I just kind of want to check. Okay, so our default bot difficulty is hard. And then let's see, as we got into agent.py, if we did anything with, okay, we did set bot difficulty to easy. So it should be capable of learning to beat the easy bot. The other thing that we probably want to go ahead and log here while we're at it, to make things a little bit easier to troubleshoot, is our epsilon, which in fact, I don't think we've even, I don't even think that we have reduced our epsilon. So what's probably happening is we're seeing random playing, and it's not going to get any better. So let's go ahead and right below our training score here, or actually let's go right above. That's fine. We'll keep these things distinct and separate. We'll do writer.addScalar stats/epsilon and self.epsilon and episode. And then down here, Again, this should all line up with your end of episode. This should not be inside of the actual episode loop, but it should be inside the total training loop. We want to do a if self.epsilon is greater than self.min epsilon. Then we're going to do self.epsilon times equals self.epsilon decay. All right, so what this should do is this should slowly decay epsilon. So if we go back, if you're not familiar with epsilon greedy, actually let me just rerun this so it's at least running while I talk. So if you're not familiar with epsilon greedy, we have our get action method. And what this is doing is this is basically saying if random.random, so random.random is going to return a value between 0 and 1. So if random.random is less than self.epsilon, then it's going to take a random action. So at the very beginning of our run, epsilon should be 1, which means we should always take a random action. As we continue the run, epsilon should slowly decrease. So when epsilon is, say, 0.5, what you're going to find is that you will take a random action half the time, and you'll take an action from the model the other half the time. When epsilon is 0.2, then you'll take a random action 20% of the time, and an action from the model 80% of the time. Our final epsilon, our min, is 0.15. So our minimum random action count is 15%. And what that does is that ensures that that is our exploration value. That is how much the model or the agent is going to explore versus how much it's going to exploit things that it already knows about. Okay. Let's see. Looks like we have an error here, and I see why. We have an error because we have not yet properly batched our inputs. So I'm going to take just a moment and find the code for that. All right, and I found my bug. So right down here, self.memory.store transition, we are basically pulling next observation here, but we're never processing it. So I need to come over here and do next obs equals self.process observation next obs. And then let's see if we're in a happy place. And we may not see it for a few episodes. Perfectly normal because it takes a little while to hit a point where we're, triggering the self memory can sample. But that is at least running. And what we should see now, let's just focus on our last run here, is we should see epsilon slowly decaying. And as the model takes over training, we're probably going to see a dip. So what I would normally expect in one of these training runs is to see a performance dip as the model takes over, because randomness will actually perform a little bit better than the model in the very beginning. And then as the model learns and performance gets better, we should start to see player one training trending up. So I'm going to pause the video and wait a little while and make sure that is what happens. All right, I'm back after about 275 episodes, somewhere in there. And as you can see, epsilon at this point is around 0.25. And we've got some really good performance from player one here. As it's training against player two, our standard bot. So this is a good place to pause and run your code and make sure everything is working correctly. If you have any training issues at this stage, if you're not seeing training kind of take off in this first few hundred steps, then you do not want to move on to the next section. Doing self-play is, again, it's more complex. There are more areas for something to go wrong than in what we're doing here, training against a bot. And I would rather you stop and troubleshoot when things are simple instead of when things get more complex. So take the time, run it, make sure it's good before you move on to the next video. This is also another good time to remind you that all of the code is going to be pushed to GitHub under tags that are aligned with the series part. So you'll see a tag for that, a GitHub tag to the code as of the end of this video in the video description. I will also post a link to the Discord if you need help. Start by referencing the GitHub, try ChatGPT, and if all else fails, join the Discord and ask there, and I or someone will be happy to jump in and try to help you figure it out. So with that, this has been a good long video. I think we are approaching an hour. I am going to go ahead and end things here. In the next one, we will pick up with a test method. So we'll throw something together to let you, test against your AI that you've trained. We'll put together some eval capabilities, and we will start working on the actual self-play mechanism to allow the agent to play against itself. So I'm going to end it here and say until next time.